Good morning. In the last class, we spoke about sampling theorem, where any band limited analog signal can be broken down into its samples, okay, at uniform intervals of time Ts, which is equal to 1 by Fs. It can then be transmitted and also recovered completely at the receiver by using these samples only if the sampling interval Ts is greater than or equal to 1 by 2W or 1 by 2 FM, where FM or W represents the highest frequency component of the message. And based on that, we spoke about the basic equations and then ideal sampling. I told you ideal sampling is a process wherein the analog signal or the continuous wave signal is sampled using impulses, a train of impulses. So we use an impulse train to sample. This is known as ideal sampling. And we wrote all the equations. Please recall the equations for ideal sampling. All this we derived, and in both time and frequency domain. And later on we said reconstruction of the signal is also possible. Correct reconstruction is possible, we showed. We showed that we'll be able to get back the message as shown, and based on that we rewrote the sampling theorem again. Okay, and then we also spoke about aliasing effect, wherein the spectrum of one component in the signal overlaps with the next component, or there is a mixing up like this. So because of this mixing up, we lose the signal. You see the signal is not taken properly or it is partially lost. This is known as the aliasing effect. Okay, and there are different solutions to this aliasing. We said we can use an anti-aliasing filter in the beginning, which is essentially a low-pass filter. So the message can be initially filtered and then we can do the sampling and transmission. Then we would be able to strictly band limit the signal to highest frequency component W. Hence, there won't be overlap or extension of the spectrum. If it's not properly band limited, it will extend the spectrum on either side, and that's why the overlap will be there. Okay, so anti-alias low pass filter will be used on the message signal initially itself. Only after that we'll do the sampling. All this we saw. Now we'll move on to a practical sampling process known as the pulse amplitude modulation, or we also call this as practical sampling. Remember, in ideal sampling, we use an impulse train, and impulse train is not permitted. In the sense, impulse train is not possible to achieve physically. You can't get impulses physically. You can get pulses of very short duration and high amplitude. Those pulses only we are going to treat as impulses. So practically it's almost impossible to design an impulse, a circuit which will generate impulses. Therefore, we can use a circuit which will generate pulses only and work on it. Okay, and we call this technique as pulse amplitude modulation. So what is pulse amplitude modulation? Very commonly asked question. They'll either ask ideal sampling. More commonly asked is this PAM, pulse amplitude modulation. In short, it is known as PAM. In PAM, the amplitudes of regularly spaced pulses are varied in accordance with the corresponding sample values of the continuous message signal. So you have a continuous or analog message signal and you're going to multiply it with a periodic pulse train. Previously we used impulse train. Now we are going to use a periodic pulse train to multiply the actual signal with the pulse train to get the sampled signal. Pulses are rectangular usually, but it can be in half sinusoidal shape and all that. You can use other shapes for pulses also. Usually we make use of rectangular pulses with amplitude A and width T or tau. Okay, you see the representation of Pam. It can be thought of as a hybrid analog and digital communication system, because here the signal is not completely digitized in the amplitude. If you observe the waveforms here, see, this is the actual message, x of t or w of t, whatever, and this is the pulse train which we are using. The second waveform is the pulse train. The pulse width is tau and the spacing between the pulses is your sampling time period Ts. Okay, so the spacing between successive pulses is the sampling time period Ts. And now when I multiply this pulse train with this message signal, what you get is the sampled signal. You observe the top of the pulses. The top of the pulses retains the shape of the message signal. So if the message signal is having some shape, that shape is retained at every pulse top. So this pulse will take the amplitude of the message and it will also retain the shape of the message at the top. That's why this is called natural sampling also, because the natural shape of the message is retained by this rectangular pulse top. So we call this technique as pulse amplitude modulation or natural sampling, where we use rectangular pulses to multiply with the message, analog message, and because we get the top of the pulse varying in the shape of the message, this is called hybrid analog and digital. Amplitude is analog in nature because we haven't cut down the amplitude short or we haven't fixed at one particular. The pulse amplitude varies according to the message. That's why this is pulse amplitude modulation or a hybrid analog digital modulation technique. And it is surely the first part of analog to digital conversion process. So in analog to digital conversion, we normally make use of such pulse trains which are generated using clocks. You see in this diagram, I have a switching device, an analog bilateral switch shown here, to which we feed in the message signal. The message signal is input as one of the inputs to the switch, and this switch is controlled using a clock. That means it will be this pulse waveform. The clock will be in the shape of a rectangular pulse tree. Okay, so the clock is nothing but this rectangular pulse tree, and the input is your baseband analog waveform, the upper one. And whenever the clock signal generates a positive pulse, this switch is closed. Whenever the switch is closed, the input is passed on to the output side. So you'll get the pulse varying in amplitude like the message and retaining the shape of the message at the top of the pulse. Okay, so it's a very simple switching circuit. We use either a BJT or a MOSFET as a switch normally here. So sample and hold experiments we do in the lab later, and you see we'll be just using a simple analog transistor, BJT or a MOSFET as the switching device. The base will be connected to a rectangular pulse train, in the sense a square wave or a pulse. You can give a square wave input or a pulse as the clock signal, and a sine wave or analog signal will be given to the collector or what, drain of the device. If it's a FET or MOSFET drain. Otherwise, if it's a BJT, you connect the message to the collector, and whenever the positive pulse comes, the transistor or the FET is on, it will pass on the input message to the output side. So you will be getting sampled signal, which is shown in the last waveform, pulse amplitude modulated signal. Okay, so this is the first step in analog to digital conversion for a practical conversion. Let's try to do a simple mathematical analysis before proceeding further. If I consider M of t as the message and C of t as the carrier, which is a periodic pulse train. The carrier is a periodic pulse train. Now, how will I represent the equation for this periodic pulse train? I can use the complex exponential Fourier series. Remember, any signal shape can be represented using complex exponential Fourier series. So, C of t, the carrier, can be represented as a summation n ranging from minus infinity to plus infinity, Cn e power jn omega naught t. Cn represents the magnitude and e power jn omega naught t is the what? It is the representation as a complex exponential Fourier. This is the basic equation. The equation C of t, what we have written, is the basic equation of representing any signal in the form of a complex exponential Fourier series. Actually, we have used this representation before when we did analog amplitude modulation. We have already used this. Now, how do I find this coefficient Cn, the complex exponential Fourier coefficient? It is 1 by the time period integral minus t by 2 to plus t by 2 or 0 to t. You can take either one of them. The given signal C of t into e power minus jn omega naught t dt. Okay, that's how you define the value of the coefficient. Now, this T naught is nothing but our sampling time interval Ts. So, I'll replace T naught with Ts and integral we take. What is the magnitude of this pulse? The magnitude of the pulse is A, right? We said we'll use a pulse train with magnitude A and time duration T. So, the magnitude of the pulse is A between minus t by 2 to plus t by 2. So, we have taken one pulse at the origin like this. Can you see? This end is minus t by 2, this is plus t by 2. Over one period you can integrate. In that one period, this is existing only for a short time. Whatever is tau or t, anything you can call the duration of this pulse. So that duration is what we have taken. And if I simplify this integral, it turns out to be, you just see the steps in simplification. Okay. So I have just substituted the limits minus t by 2 and plus t by 2. Then in order to get 2j beneath, I have minus j. To make it plus j, I have shifted this minus sign here. So this term comes first. E power jn omega naught t by 2 comes first. Minus of e power minus jn, which is the needed form for a sine wave. And to get that 2j in the denominator, I'll take 2 in the numerator. So this whole term turns out to be sine n omega naught t by 2 or tau if you take it, tau by 2. Next, I want to bring it in the form of a sync pulse. So for sync, I should have it in the form sine what? Pi theta by pi theta. You should bring it to the form sine pi theta by pi theta. So I'm just substituting for omega naught as 2 pi fs. Wherever we have omega naught, we are substituting 2 pi fs. Okay. And after simplification, actually we had done this in the initial classes only, if you remember. A rectangular pulse, we have already found the complex exponential Fourier series representation, the Fourier series for a rectangular pulse train. Same thing we have repeated here, nothing special. All what I have done is, I have found the Fourier series of a complex exponent, Fourier series of a periodic pulse train. Okay, rectangular pulse train we have found. We had already found it would be in the form AFS T or tau, you could call, sync NFS T. So this is the value of the Fourier coefficient. Now you can substitute that in C of t. What will you get C of t as? AFST sync NFST into e to the power of j2 pi n omega naught t, which becomes, let's say j n omega naught t is, instead of omega naught, 2 pi fs we have substituted. This will be the expression. And if you want the sampled signal, how do I get the sampled signal? See, first you write the expression for C of t here. I don't have a pen with me today, so please make careful note. This C of t will be Cn into e power jn omega naught t with summation from minus infinity to plus infinity. And we have found Cn is this. So what we have done next, for C of t, I have substituted Cn into e power jn omega naught t. For omega naught, I have substituted 2 pi fs. And next, how do I get the sampled signal? Remember, sampled signal is obtained by multiplying message with the periodic pulse train S of t. So m of t into the pulse train C of t gives me the sampled signal S of t. We are calling S of t as the sampled signal, the last signal which we had represented. Okay, and the message signal was m of t and the pulse train is C of t. So I have just substituted the value of C of t here, and m of t we have kept as it is, it's a product. So C of t is represented by this first part of the summation. AFST sync NFST into e power j 2 pi NFST. This whole thing represents the carrier, which is a rectangular pulse train. That multiplied with the message m of t gives you the sampled signal S of t. Okay, and we call this as naturally sampled signal, I told you before. So you can name this as equation 1. Now the next step is to take the Fourier transform so that I'll get the frequency domain representation. So S of t is replaced with S of f. A, F, S, T are all constants brought outside the summation. Then inside the summation, I have sync, this should be sync, summation minus infinity to plus infinity, sync NFS T. And what is the Fourier transform of e power j2 pi NFS T into m of t? See, e power j2 pi NFST has a Fourier transform delta f minus NFS. Actually, we have again derived this in the beginning. What is the Fourier transform of a rising exponential? This is rising exponential. It will be a right shifted impulse. And by how much will it be shifted right? By the amount specified in this exponent. So, the Fourier transform of e power j2 pi NFST will be delta f minus NFS, and the product operation becomes convolution in the frequency domain. Remember, a product always changes to convolution. A convolution becomes a product when I convert from time to frequency or frequency to time domain. Okay. So now this becomes convolution. M of t has Fourier transform m of f. So we get this equation which can be simplified one last step, that is any given signal convolved with impulse will result in the signal existing where the impulse existed. So convolution of an impulse train with any signal would be the same signal existing wherever the impulse existed. That's all we have done in the last step. F, AS, A and T are all constants. Summation minus infinity to plus infinity for n. Sinc NFS T, and this term within brackets becomes M of F minus NFS. Now, how do we represent this S of F? If we have a triangular spectrum for M of F, remember M of T is a band limited signal. So, if M of F has a triangular spectrum, which we usually write for any band limited signal, then S of F will be the shifted versions of these triangular spectra M of F, but also scaled by the factor sinc NFST. Remember, this sinc NFST is getting multiplied with M of F minus NFS. So it is not just shifting the message to all the points, integral multiples of the sampling frequency Fs, but it is also scaling those by a factor sinc NFST. That's what I have shown you in this waveform. So S of F is represented, the sinc signal I have drawn as a dotted line, and the spectrum of the message we are showing, which exists at 0, Fs, 2 Fs, so on. Okay, so this will be the representation of the sampled signal in frequency domain. So the simple mathematical analysis tells us how we are going to represent the carrier. The carrier is a rectangular periodic pulse train. So the carrier is represented using the standard equation for a rectangular pulse train. And in a rectangular pulse train, the coefficient, the Fourier coefficient is given by a sinc function scaled to a given amplitude. So once we have that carrier representation, we'll take the message and multiply it with the carrier, which can be shown here. They have taken the same thing, but the representation is slightly different. That's all. Okay. Now, next we'll move on to demodulation of gated Pam signal, in the sense here, yeah, any doubts? See, the naturally sampled signal is available at the input, and at the receiver I have a local oscillator, and both these are multiplied using an analog multiplier, and the result of this product is passed through a low pass filter. This low pass filter has a transfer function h of t in time domain or h of f in the Fourier domain, frequency domain. So whatever resulting value you get, that is called the demodulated signal. Anyway, we'll go through that little detail later. We'll be doing it in order. So, can somebody tell me what is the problem with natural sampling? Anybody think over and tell me what may be the problem with natural sampling? Yeah? In natural sampling, what happens? What exactly happens to the pulses in natural sampling?
Continuous amplitude.
Yeah, the pulse top varies continuously with the message. And remember, I can't transmit the signal as it is. If I'm going to convert it to a completely digitized signal, say I have binary representation for the top of each of the pulses. Now, whatever value you will have at one end, say if you take that value and try to represent it digitally, the value here is 5, for example, 101 was the digital binary representation, and this pulse amplitude is raising, at the other end it becomes 6. So that will be digitally represented as 110. You want to know whether you should consider the beginning or the end or the middle. You will be confused, and as long as that top of the pulse is fed to an ADC, analog to digital converter, it will give you fluctuating readings because the amplitude doesn't remain constant. In natural samples, the amplitude is varying. Because of that, when you try to apply it to an ADC, you'll see that the digital output will also vary continuously because of variation in the amplitude of the pulses. So what we do to avoid this, we design something called as flat top samples. We don't want the pulse amplitude to vary along with the message, but we want the pulse to remain constant once it reaches that sample point, the analog sampling point. It should take a sample and it should retain that level. It should not vary the level according to the message. If we are able to do that, then you have sufficient time that the output will remain in one state and the ADCs can work efficiently. ADCs will give you one answer for this value instead of multiple answers because ADCs are faster, and by the time ADC gives some output, this amplitude would have changed. So ADC will again change and give you another output, the analog to digital converter. So since that shouldn't happen, we are interested in maintaining the top of the pulses as a constant value. And this kind of sampling is called flat top sampling. So what is flat top sampling? Flat top sampling is a method of sampling the analog signal using pulses which maintain the flat top or which do not change according to the message. The top of the pulses should not vary according to the message, but it should remain constant. So the top of the pulses should remain flat or constant. Okay, this is called flat top sampling, and we'll try to analyze this. So notice what are the representation. M of t is the message signal, S of t is the what? Sampled signal, and t is the width of the rectangular pulse. You see the rectangular pulse has width t, and ts is the time period between two pulses. The sampling time or time period between two pulses is ts. Okay. Now let's see how do we realize this PAM or flat top samples. First, we try to do instantaneous sampling of the message signal once in every ts seconds or using a sampling frequency of fs. And this fs will be greater than or equal to 2w according to sampling theorem. Okay, the minimum required fs should be greater than or equal to 2w. Next, so once we do instantaneous sampling at the given frequency rate, we try to lengthen the duration of each sample to obtain a constant value t. I want the impulses to be converted to pulses. That's all I'm trying to do. We initially sample the given message signal using impulse stream, and now I'm trying to lengthen the duration of the impulse. I want to convert impulse to a pulse. So I want to change the duration of that impulse to have a constant width t. These two clubbed together are called sample and hold circuits. In the sense, first do ideal sampling with an impulse train, Then you pass on that through a system with impulse response h of t, so that you will drag the duration of the sample taken to a finite width t. Sample with impulses, then convert that impulse to a pulse using a system having transfer function or impulse response h of t. We call these two put together as sample and hold circuits. The question is, how long should the pulses t be? Generally, we assume the pulses t to be as small in width as possible. We don't want very huge width pulses, because then we can't accommodate more number. Whenever I want more number of sampled pulses, I should take the pulse width to be small. Okay, let's derive this. Let S of t represent the sequence of flat top pulses which is generated using the previous description. Then we are going to get S of t in this form. We'll derive this. This equation 3.10 will be derived. We'll see what this equation states. Ts is the sampling period and m of n ts is the sample value or the scaling value for the sampled signal. So the time period for sampling is Ts. The amplitude or scaling factor for the sampled signal is given as m of nTs. Okay, and it is at the value at the time when t is equal to nTs. So how do we represent the standard rectangular pulse? I am showing you the circuit here in the sense the block diagram. Here the input to this system with impulse response h of t is considered as m delta of t. Do you remember what was this m delta of t? Or g delta of t we called it as, I think. We called it as g delta of t in ideal sampling. It represented the ideally sampled signal. So when g of t, the message was multiplied with an impulse train, what was the result you got? That you called it as g delta of t. The same convention is used here also. Here the actual message is m of t, and when it gets multiplied with the impulse train, it becomes the sampled signal m delta of t. Okay, so I have the instantaneously sampled signal m delta of t. I am going to pass it through a system having impulse response h of t, so that you will get the sampled signal s of t at the output. And how do I represent the impulse response of a rectangular system h of t? We say its value is 1 between 0 to t. So for the whole width of the pulse, the value is 1, and at the points where the pulse goes down, the value becomes half and it is 0 elsewhere. So you have imagine a straight rectangular pulse. That rectangular pulse has amplitude 1, okay, at the interval between 0 to t. The t represents the width. So between 0 to the given width t, it has an amplitude 1, and it will have the amplitude half when it is going down from the maximum. And this happens when t is equal to 0 or t is equal to t. So at this point, when it is rising or falling, we'll consider h of t value as half. And lastly, in all other places where that rectangular pulse is not there, it is 0. So this represents the impulse response of the system, to which we are feeding the what? The impulse sampled signal m delta of t. So m delta of t is sampled using impulse train that is fed to a system having h of t. Therefore, the sampled signal s of t is given as input m delta of t convolved with the impulse response of the system h of t. The output of this system is s of t is m delta of t into h of t, and the instantaneously sampled version of the signal, we have already derived this, so let us directly take the equation. How can I represent this instantaneously sampled signal? M delta of t is represented as a summation n ranging from minus infinity to plus infinity, m of nts delta t minus nts. This we derived when we did ideal sampling. Okay, the same equation we are considering, and delta t minus nts represents the time shifted delta function. Okay. So now after convolution, we are going to convolve. All this is just derivation or simplification. So just observe correctly what is happening after convolution. You just see m delta of t convolved with h of t. It becomes integral. How do I represent a convolution? It is integral m delta of tau h of t minus tau d tau. And for m delta of tau, I already have the value here. This last equation, m delta of tau, we already have the value. So it is m of nts delta t minus nts or delta tau minus nts into h of t minus tau d tau, which is m of nts. We are interchanging the positions of integration and summation. Now, what does this term within the integration refer to? Can you take any guesses? Delta tau minus nts into h of t minus tau can be written as h of t minus nts. Why? Again, using the shifting or sampling property of the impulse function. So, what does this represent? This term here within the integral. It represents the convolution operation of this shifting impulse with the signal h of t minus tau. So you have the input which will be what? The impulse train, shifted impulse train multiplied with h of t minus tau and integrated from minus infinity. This means convolution of h of t with delta t minus nts or the shifted versions of delta. So you just perform a convolution operation, means you know the product of any signal, the convolutional product of any signal with an impulse or impulse train will result in that signal existing where the impulse existed. So this h of t minus tau will change to h of t minus nts. Now, this is nothing but the convolution of the ideally sampled signal with a system having a rectangular transfer function having impulse response h of t. The result in the previous slide means that the Pam signal can be mathematically written like this. It's the same equation. Okay. All what we are trying to do is we are trying to show the sampled signal could be written like this, which is nothing but convolution product of the ideally sampled signal using impulse train and then passing that signal through a rectangular filter with transfer function h of t. So, if you observe the right hand side, both are same. What does this mean? This means that the sampled signal S of t can be written as m delta of t convolved with h of t. In the sense, I was trying to prove that if I ideally sample the given analog signal, and then extend the duration of the sampled pulse to a width t, I am going to get the sampling signal. And the same thing we are getting here. Okay. So we are able to get the sampled signal S of t, which is m delta of t convolved with h of t. Now you take Fourier transform on both sides, you get S of f. Remember, convolution becomes multiplication. M delta of t becomes m delta of f, h of t becomes h of f. So this is the effect of taking Fourier transforms. Now, using this in the relation between m delta of f and m of f. Remember, when we did ideal sampling and when we tried to do reconstruction, we showed how we could get back m of f, the message spectrum from the sampled spectrum m delta of f. So we'll try to use that. We knew m delta of f was fs summation m of f minus kfs or f minus nfs, whatever you want, you can take. Okay. This is the representation for m delta of f, which we did when we considered m delta of t. Now, final substitution, we get S of f expression as fs summation k is equal to minus infinity to plus infinity m of f minus kfs h of f. So, when we have to multiply m delta of f with h of f, we are substituting for m delta of f, which we obtained when we did ideal sampling, and we are multiplying it with h of f. This represents the Fourier transform of the Pam signal. So we wrote the time domain representation of the Pam and then the frequency domain representation or the Fourier transform of the Pam signal. The next part here is the recovery procedure. So how to, till now we got the sampled signal. The first part is getting expression for the sampled signal. In this case, it is the PAM, pulse amplitude modulated or naturally sampled signal in time domain and then in frequency domain. And later on we converted, we don't want natural sampling. We said we want a flat top sampling. In order to get flat top sampling, what we did? We took the ideally sampled signal and passed it through a rectangular filter having amplitude A and width T. So when you sent the naturally sampled signal through a rectangular filter, it converted all the samples to flat top samples. That's what we have done now. So passing this ideally sampled through a filter to extend the time duration and amplitude to get the required amplitude and time duration is the procedure used to get flat top samples. Now, once we have got the flat top samples, which we have represented in both time and frequency domain here, this is the frequency domain representation and the time domain representation was shown here. Now, we have to check how we can recover back the original message. What is the procedure for recovery? After sampling, we move on to we transmit that signal and we move on to the receiver to check for recovery. Assume that the message is limited to bandwidth W and sampling rate is Fs, which is higher than the Nyquist rate. So Fs should be greater than 2W if it should be higher than the Nyquist rate. Okay. So pass the received sampled signal S of t through a low pass filter whose frequency response is as shown. So the frequency response of the low pass filter is like this. It has a pass band from minus W to plus W and transition band from W to Fs minus W. Okay. So this is the result obtained. And how do we derive this? So to determine the Fourier transform of rectangular pulse, which is plotted in the figure. Let's consider h of f. The response to be what? How do I take Fourier transform of a signal? Integral h of t into e power minus j 2 pi ft dt. That's how I'll get h of f. Okay. See, the signal h of t is like this. It's a rectangular pulse, and to get h of f, I have to integrate it between minus infinity to plus infinity. And here that rectangular pulse is limited to a duration of t. So the width of the pulse or the duration of the pulse is t seconds. So I'll replace that minus infinity with 0 and plus infinity with t. That means we are starting a rectangular pulse at 0 time and ending that pulse at time t. You can also do it from minus t by 2 to plus t by 2 like how we have done before. Even that you will get the right expression. Okay, so you can take the rectangular pulse, then it is equally split about the vertical axis at 0. Here it starts, the pulse starts at 0 and ends at time t. That's why we have taken the limit 0 to t. And what's the value of that pulse? The value of that pulse is supposed to be 1. You can also consider A, but here we'll take the amplitude of the pulse to be 1 to help us make it easier. And the Fourier transform is e power minus j 2 pi ft dt. All what I'm doing next, you please observe these steps. There is no point in me describing it. Simplifying it. Please observe how we have simplified. The integral, what does it become? Then apply the limits 0 to t. So once you apply the limit 0 to t, what happens to the equation? The next step is to what? Convert this to the form of a sine and a sinc pulse. So to convert it in the form of sine, I need it like this. E power j pi ft minus e power minus j pi ft by 2j. For that, whatever I need to multiply or divide, we'll do it. So what is left outside is e power minus j pi ft into sine ft. Okay, or sine pi ft, I can say. This is sine pi ft. And in the next step, what I'll do, I already have a pi f in the denominator. So I'll multiply and divide with the time t. You see the capital T here. Multiply this with t and also divide. So what you will get? You will get sine pi ft by pi ft, which becomes sinc ft. Remember, sine pi x by pi x is sinc x. Sine pi ft by pi ft is sinc ft, and we already had a t to be multiplied, and this e power minus j pi ft is already there outside. So this represents the value of the transfer function h of f, which is the transfer function of the rectangular pulse. So the rectangular pulse in time domain has response h of t, in frequency domain h of f, which is given by this equation, t into a falling exponential e power minus j pi ft into sinc of ft, a sinc signal. Okay, so based on this, how do I write the sampled signal spectrum? The sampled signal spectrum S of f is what? M of f into h of f, right? M of f into h of f, we had shown here. M delta of f into h of f. So that m delta of f into h of f is what we have written here. M delta of f we know is fs summation n minus infinity to plus infinity m of f minus nfs. So this first part is the value of m delta of f. The second part, t e power minus j by ft sinc ft is the value of h of f. Therefore, we have realized this. Please understand this equation 3.16 is what we have realized. So m delta of f is given by this equation, fs summation k minus infinity to plus infinity, m of f minus kfs, and then h of f we have shown how we can represent. H of f could be represented like this. This represents our recovery equation. The final equation what I had written there, this equation represents the recovery equation. Okay. Now, let's summarize what we have studied. The flat top samples are used here, and if we use flat top samples to generate a pulse amplitude modulated signal, we are going to introduce an amplitude distortion and delay of T by 2. So what do you mean by amplitude distortion and delay? So here the amplitude does not remain constant. You see the amplitude varies as t into e power minus j pi ft into sinc ft. So I have a sinc function, a falling exponential, all this into time period t, everything is multiplied to this train of pulses. M of f minus mfs represent the train of pulses. To that train of pulses here, we have multiplied some amplitude. So we can say there is an amplitude distortion and there is a delay of t by 2. This distortion is known as aperture effect, and it is corrected by using a circuit known as equalizer at the receiver. So at the receiver, we use equalizer after the low pass filter to compensate for this amplitude distortion and delay and aperture effect, whatever it is known as. And what should be the magnitude of this equalizer filter? We are going to add an additional circuit known as equalizer. That equalizer should have the magnitude response which is 1 by that of h of f. See, the distortion is caused by this factor h of f only. See, h of f has t e power minus j pi ft sinc ft. This whole term distorts the amplitude of the pulses. Otherwise, the pulses would have remained m of f minus nfs properly. But getting multiplied by this factor is distorting the amplitude, and because of that I have to use an inverse equalizer circuit to the what? To the circuit which we used at the transmitter. At the transmitter I used a system with impulse response h of t, and why did I use that? In order to get flat top samples. Without using that, I would have only impulses. To extend those impulses and get flat top samples, we made use of a filter having impulse response h of t at the transmitter. But its effect at the receiver is to add aperture effect, which means it causes amplitude distortion and also a time delay. That amplitude distortion and time delay at the receiver, which is due to the addition of h of t system filter at the transmitter, can be overcome by using a system known as equalizer with inverse transfer function 1 by h of f, 1 by t sinc ft. This I have to use. And see, this is how we represent the transfer function h of t, the rectangular pulse. Its amplitude 1, time duration t, and it goes to 1 from 0 at 0 and it comes back down at t. So at 0 and capital T, the amplitudes are half. And how does this h of f look? This equation we are trying to represent, this equation, the last one, you see t e power minus j pi ft sinc ft. How is that represented? We take only the amplitude response. So that sinc signal, instead of going down, it's coming back on top. When I consider just the amplitude, h of f looks like this. You see it will touch 0 at every 1 by t, 2 by t, 3 by t, so on. Its phase response is like this. The phase will vary from plus pi to minus pi as the signal varies from one time period. Okay. So this equalizer is used in reconstruction. So with this we'll conclude PAM. Transmission of PAM signal imposes strict requirements on the magnitude and phase responses of the channel because of the relatively short duration of the transmitted pulses. And noise performance of a PAM is bad. It can never be better than normal baseband transmission. So without doing any modulation, if we just want to transmit the baseband signal, whatever performance you get, PAM signal will be almost similar to that, not much of improvement. And PAM is normally used only in time division multiplexing and later on for long distance transmission. Other versions of pulse modulation are used. PAM is not preferred for long distance transmission. Okay.